Example problem 2. Two strings with linear densities of 5 grams per meter are stretched over pulleys adjusted to have vibrating lengths of 50 centimeters and attached to hanging blocks. The block attached to string 1 has a mass of 20 kilograms, and the block attached to string 2 has a mass m. When driven at the same frequency, the two strings support the standing waves shown. A, what is the driving frequency? And B, what is the mass of the block suspended from string 2? Okay, so the first thing we want to do is set up our list of knowns. We see that we have linear densities of 5 grams per meter, or let's put that in SI units so I don't forget later. That's 5 times 10 to the minus 3 kilograms per meter. Stretched over pulleys adjusted to have vibrating lengths of 50 centimeters, so both of them have a length of half a meter, and attached to hanging blocks. The block attached to string 1 has a mass of 20 kilograms, so M1 is equal to 20 kilograms. And I'm going to call that M1, string 1, right? And the block attached to string 2 has an unknown mass M, so I'm going to call that, and these are all capital M's. I got to be careful because string 1, right, has a mode number, M1, I guess I could call it, little m, and that's mode 1, right? This is vibrating in the fundamental mode. Here we see M2. Oh, yes, for string 2, the mode is actually 3. We're in the third mode here. Where was I? When driven at the same frequency, so that means I'm going to call it F1 is equal to F2 is equal to F. I'm just going to call it F. The two strings support the standing waves shown. Okay, and I want to write down my mode numbers for each of them. So M1 is equal to 1, and M3, the modes are here. Okay, so part A, what is the driving frequency? I'm not sure if you can see the orange well. So A is asking, what is F, the driving frequency? Well, I can find that because I know the driving frequency, the frequency at which my string oscillates, is related, right, to the mode number. So here's my mode number M times the speed of the wave on the string divided by twice the length. So then I need to find, I have the length, right, that's there, but I need to find the speed, which is given by the square root of the tension in the string divided by the linear mass density. The linear mass density I'm given, that's nice, but the tension I need to find. So the tension I can find from Newton's second law. We know our mass is in equilibrium, which means the tension pointing upward is equal to the weight of mass 1 pointing downward. And because we're a simple string over a pulley, that tension is the same everywhere along the string. So I can say a little side note here that the tension is equal to M1, capital M1 times G. So I'm going to plug that in here, and I'm going to plug this in up here, and I see that the frequency, in this case, sorry, we are in mode 1. Oops, let's erase that. Good. Go back to that one. So F1 is equal to 1. This is all for string 1. 1, that's M, times V. V is the square root of the tension. The tension is M, big M1, G over mu, times 1 over 2L. Okay, everybody see that? So now I'm ready to plug in numbers. So 1 is 1. I get the square root of M1 is 20 kilograms times 9.8 meters per second squared divided by the linear mass density, 5 times 10 to the minus 3 kilograms per meter. And this is all under the square root times 1 over 2 times half a meter. Now, I can take a look at the units. Kilograms cancel. I get meters squared over seconds squared to the 1/2 becomes meters per second. The meters cancel, and I'm left with inverse seconds, which is a hertz. And if you plug this into your calculator, you should get 198 hertz, or at least that's what I got for the driving frequency. Good. Now for the second question was asking, what is the mass of the block suspended from string 2? So find m. Well, I can actually do this. Just add another page, append page. Yes. I can do this by basically going backward from the same procedure that I just did here. So I'm looking for m, or m2 if you wanted to call it that. So in this case, well, let's see. I'm going to take this expression, right? So f sub m is equal to m times v over 2L, but my v is the square root of tension in the string over the linear mass density, times 1 over 2L. But in this case, right, by the same logic as before, my tension in the string 2, so in string 2, the tension is now equal to the unknown mass, right, times the acceleration due to gravity. Kind of makes sense. So I'll plug that in here, and then I'm going to have to rearrange everything to solve for m. Okay, so little m, though, little m, remember, that's the mode number. That's little m. Oops, that's supposed to be a 2 here. 2. Little m2 is 3 because string 2 is in the third mode. I hope these subscripts aren't getting confusing. So basically, we want to rewrite this as F3 is equal to 3 times the square root of the unknown mass times g over mu times 1 over 2L. Solve for m. So let's see, this becomes, I'm going to move that to the other side. So the square root of mg over mu is equal to 2L F3 over 3. Now I can square everything. Dun, 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 dun. And I get mg over mu is equal to 2/3 L F3. Now this F3, that's just the third mode frequency, but that is the same driving frequency that we found in part A. So let's not forget that. So I can now solve for m. That's equal to the linear mass density over the acceleration due to gravity times 2/3 L F3. All that squared. Now I can plug in numbers. My mu was 5 times 10 to the minus 3 kilograms per meter, divided by 9.8 meters per second squared, times 2/3 times half a meter length, and the frequency was 198 hertz. Don't square all that. And if I didn't make any mistakes in my calculator, hopefully you'll end up with 2.22 kilograms. Let's check the units. I have a meters squared over seconds squared here. Outside, I have a second squared on top and a meter squared on the bottom, so the meters and the seconds all cancel, and I end up just with kilograms. So that looks good. Now, let's assess this for a moment. Does this make sense that I have a smaller mass hanging when I have a higher mode number? Well, if we take a look at this expression here, we see that if we increase m, right, the mode number from 1 to 3, right, first fundamental mode to the third mode, then the speed of the wave must go down. How can we make the speed go down? Well, if we decrease the tension or decrease the amount of mass that's hanging, we can do that. So hopefully this is what you saw in your lab last week as well. All right, see you in the next video.